y empezamos a desarrollar 5 o 6 proyectos y 3 de ellos ya con fondos para tener estudiantes graduados. Y digamos que mi presentación es en cierto modo en conocer colaboradores internacionales, especialmente de Argentina, para ver en qué podemos trabajar juntos en algunos proyectos que sean relevantes para ambas instituciones. So, ahora. One of the things that I'm more interested is on numerical weather predictions for power generation and for energy management. So I'm going to start briefly with the history of meteorology, because that's actually what connects you and I on this topic. And probably you are familiar with this type of maps that probably you did by hand, maybe not anymore. But in the 10, 20 years ago, that was a typical synoptic map that we had to draw with observational data. At that time, we did not know that, but we actually were developing what is called now data-driven methods. That means just by purely observing and identifying space and temporal patterns, try to find a way to predict out of the data itself without a numerical model. So notice here the date of this map, which is October 1922, so almost more than a year, 100 years ago. So if you're familiar with these maps, keep that in mind, that for more than 100 years, people have been studying these systems. Moving forward, 100 years later, we now have operational systems that develop this automatically every 15 minutes in the best of the cases. And we are very glad to be on this generation of users of quite sophisticated models. We still are aiming to improve these products, we call them products or guidance, in terms, and we measure them in terms of accuracy, resolution, and in how much information they contain, and how fast or how in advance we receive those products. After 60 years of numerical weather prediction, we wonder on these simulations that are quite realistic. And here you can see, this is a simulation from the NCAR, the WRF system, with trajectories of air parcels showing diabatic heating, and in colors is the potential temperature. If you, for instance, stop over here, this is a Hurricane Sandy, and it shows the trajectory, the intensity, and then the dissipation. If you stop here, for instance, you can see that the parcels go downward, inducing what is called a geostrophic flow, which is opposite, so tries to create this isothermal wind balance, and so it produces upward motion and downward motion here. So those are aspects that are not only important in terms of increasing our knowledge of the phenomena, but also for practical values, we can see that we could implement products that could be more informative. In terms of storm forecasting, there are, at the national level, 3 strategic goals. One is to improve the accuracy. That means reduce statistical errors. After numerous cases they put together, and they want to continue this decrease in terms of the error magnitude for different forecast lead times, 24 hours, 48, 3 days in advance. So the National Weather Service aims to continue this rate of decrease. And so this is one special strategic goal. The second is increase realism in the modeling. And that means increasing model resolution. And we have here a community multi-scale model that resolve even the microscale. And then the third one is preparing products that provide warning systems that provide the information used for the ultimate users. So those are three aspects that have been goals for many years, and I would like now to take on these strategic goals and map it into what could be the goals for instance, the new trend of renewable energy, which is photovoltaic energy. And here you see a panel of solar energy collectors. And on the right, you see a time series from this is the time of the day from 6 in the morning to 6 in the afternoon. For one site alone, you can see the intermittence, that the flow of energy is not continuous. This is a time series of every 20 seconds location. This is a big problem for managing energy that fluctuates that much and very rapidly. What people tend to do is collect many PV panels from different locations, and so you aggregate them in such a way that you get kind of a smoother, and you see the red line now slightly smoother because you aggregate the combined energy. But this is not enough, because the current tendency is to have now panels on the rooftop of houses and also manage the energy at the local level. So you return again to very high fluctuations that are in a barrier to really utilize the entire energy. So in terms of timescales of what is needed for numerical weather predictions for solar energy, or in general renewable energy, it's you can see the timeline, and what is needed is to have from seconds to minutes to understand the energy variation. And in this case, it's important to take into account that at this level, basically meteorology is ignored. So these are just turbulence, and these might be other methods that needs to be used, at least for now. However, there are some ramps, what we call, that we continue to study, and people have realized that these sudden changes in the energy generation, for instance, are related to gravity waves, which we usually ignore. And so this could be something that opens the door into detecting these eddies or these organizations in wind or in solar and so on. Here I put a photograph of people who use the weather to make decisions on the dispatch of energy at the hourly, or which we call it real time, and at the day ahead. So one day ahead, they commit certain units to be deployed, or if you are burning gas, for instance, you are ordered to do or committed to do that in advance. So they need to know both the weather, and also they need to know what units are available and how long it will take to get it online. So it's a very sophisticated procedure. Most of the time, schedulers prefer to err on generating an excess of energy rather than needing energy. So that's one of the savings that weather forecasting could have, to make more efficient the use of of both renewable energy and to reduce gas-driven or thermal electric energy generation. The other aspects is the use of other sensors. So I mentioned that currently people are using, including on our team, we are running some mesoscale models and computing bias correction. But I think more than that, and the intention is to have, with the WRF model, this range of uncertainty in the drop of energy production due to clouds, for instance. So we have here, this curve means the incoming energy from the sun. This gray color would mean if there were no clouds, we call it clear sky conditions. But if there are clouds, then there is a drop in the energy production. But the main question is how much it would be. So computing a deterministic calculation of this might be impossible for mesoscale models, but probably the range of uncertainty might be feasible. One of the things that we are adding to the observations, to the conventional observations, are the use of whole sky cameras. So we got a network of cameras that are monitoring the sky, and we intend to collect a large enough data set to start creating data-driven forecast of cloud cover, and at the same time and also cloud motion vectors from the cloud motion to determine the net radiation falling onto the surface on particular locations. So that's one of the tasks that we got funded for in one of the projects that I mentioned before. We are also advancing the resolution. So we developed already an LES system that produces this type of realism in the cloud formation. So we are also in contact with some private companies that have nano satellite data, and our intention as a team is to collect these observations to create what is called tomographic reconstruction of clouds. So this is still an ongoing. It was funded now for Yukon as a seed project, just to start analyzing both data, both the large eddy simulation and the satellite data, to see how we can combine them. In the long term, we wish we could do a data simulation scheme using large eddy simulations, but I think we are we still need to be able to organize the data first and do quality control and so on. Another project that is also taking place here in the New England region in the US is the offshore wind industry. And so we are developing the numerical infrastructure to do predictions of the amount of energy that it's going to be generated. So we have set up the WRF system at different resolutions, horizontal resolutions, and we have now an experimental nested with three nested actually WRF system. The one in the interior is grid 4, which has a resolution of 200 by 200 meter. These are very expensive, computationally expensive runs, so we have only a few weeks, or we are actually doing that on demand to get to calibrate the model depending on what parameters to use. The main issue, and these are the main issue we have. First, the motivation is because here in this shaded blue area is where the wind farms are going to be located. So that's the target for the high resolution wind simulation and forecasting. The problem we have is that we don't have observations. So except for one or two LiDAR observations, it's very hard to really get into validating or making sure that the model is providing the correct forecast. So that's one of the motivations to move into other projects that we are actually combining with this one. I'll explain in a minute, but before that, this is the model that we are developing at UConn, which is an explicit turbulent model that is quite realistic in terms of cloud formation, cloud dynamics. The intention is to use this with what we call it actuators, which affect the wind flow and produces what is called the wake effect. The wake effect is very important for the industry because it not only reduces the efficiency of the extraction of energy for the second row of wind turbines, but also induces damages because of vibration. So those are aspects that the industry are very concerned. They would like to have quantitative values depending on the weather conditions. So we did that. We added an actuator network, a network of actuators here, and we display in color the wind speed, in this case the zonal wind speed, and this is what we get for different layouts. So we can modify this the location of the wind farms to identify, depending on the prominent wind field and wind conditions, to determine what are the impact with the downstream rotors that are placed here. Here is the same model simulations, but with this is a vertical cross section of our simulations. In addition to numerical models, we are working on 4 areas of data-driven modeling. One is the study of wind power ramps. Because of the time, I cannot present on that, but the intention is to extract, we have a method to extract ramps. Ramps are sudden changes in power, either from low power to high power, or we call it ramp ups or ramp downs when it goes from a very high or high generation of power down. So those are important conditions for managing, because those could happen in less than 5 minutes or even in minutes. And so detecting them at least is something that is important. So we are studying mesoscale models to see whether they are capable to at least to detect these rapid shifts in power. Another thing that I want to mention is that wind power goes to almost the cubic of the wind speed. So any change in the wind speed produces a very large power ramp. The second topic is about using purely statistical methods. A method is called change point detection, which is determining at what point, or the breaking point of a tendency. So if you have certain wind fluctuations, and all of a sudden you see that fluctuations start to increase, then you have a change point in the behavior of trend behavior of the time series. And 2 more others related with machine learning. The other projects is about regional modeling for coastal and marine environments. this project has been recently funded by NOAA, and NOAA is the National Oceanic and Atmospheric Administration, and they are in charge of developing the next generation models. So we are particularly, or the objective of this project, in which 7 groups have been the joint efforts, is to advance the technology of data simulation for real-time mesoscale analysis. And we intend to combine the 3 systems: the wind, the waves, and currents. So this is I would say semi-coupled data simulation, because what we are going to do is only couple the waves with the winds, and then just do a nudging with currents. So for now, we don't attempt to do in this 3-year project to do a fully coupled data simulation, because it might be very complex. One technique that we would like to add into the workflow is do bias correction of the field itself. And here is a diagram of what we intend to do. The general concept is that when you have and this image reflects whales, one of the whales flaps, and you are going to compare a first guess. Suppose that this red color is a first guess with the observations. So you have the observations like this, and they look like, I mean, visually they look similar, but they are just distorted in some way, positionally. So the intention is to, or what we do in our technique, is to split this into several steps. One is to scale, then shift to position, and then rotate, for instance. And so it creates an alignment, and we tested that and published a paper on how we did the field alignment technique. And the intention is for storms that are localized. So you can see as features, when you do the root mean square errors, if this is a positional error, then the problem is it produces what is called the dipole. This basically reflects that is shifted. If we use this field alignment technique, what we do is we determine the displacement vectors. So these displacement vectors helps into creating this new system, so we can compare with each other. And then when we do the root mean square errors after this positional, only the positional aspects, we get a decrease in the root mean square errors for this tropical hurricane case. We are also collecting and doing analysis of multi-mission satellite data. So we are collecting all the satellite altimetry that is available to us to create maps of data for our region of interest. We have not used this yet as a data simulation. We are just collecting data and producing what is called objective analysis as a first step, just to make sure that this is the winds and the waves in this case are consistent with each other. In addition to the satellite altimetry data, and it's to use the other resource which is available worldwide, which are the low-cost, high-frequency radar. This is basically an antenna, not very expensive, that many oceanographers use to compute significant wave heights and also offshore wind. And so we are combining this, both the satellite and the high-frequency radar to create consistent wind fields and also waves. Another thing that we are advancing is improving or actually testing new underwater acoustic sensors. So both the National Institute for Undersea Vehicle Technology and the big energy company is they are interested on developing, or they already have some very expensive systems to collect acoustic sensors. And so we are working on low-cost sensors that could be used for many multi-purposes. With the echoes or with the signals, acoustic signals, one could determine, depending on how close they are, they can determine whether there is a ship movement, rain, whales, all the phenomena that produces sound, like bubbles produced by wind or wave breaking. So these sensors are capable of distinguishing out of the noise, distinguishing those signals. So what we are doing in our project is to connect these underwater sensors with a miniature buoy, also a very inexpensive buoy that transmit to cell phones or satellite and have now real-time observing networks. So we were awarded funds to establish 5 or 6 couple sensors of acoustic and surface variables. The intention is to use it for the offshore wind industry to determine the impact or potential impact of construction on the marine environment, for instance. The pile driving, when they do construction, they need to drive a pile into the seafloor. And so this rapid hammering of this concrete into the surface produces not only very strong sounds, but also at certain frequencies, so we call it peak pressure, that might induce damages in some marine animals that rely on acoustics. The other aspect that we are interested in is on targeted observations, and I can explain a little bit on this. The intention is to establish a network that interact with each other. So the information that is received simultaneously by the 4 sensors or 5 sensors could be integrated to do, again, like tomographic reconstruction. So those are plans that we will start in the summer of next year. And we hope to have more collaborators on using the data to extracting signals at the surface. I'm going to go, depending on how much time, I think I have more time. Now I'm going to shift a little bit into the energy management systems. So those are outstanding problems that we would like to address. Sometimes these are totally different fields to meteorology. So when I interact with these engineers, they are surprised to see that we also have techniques that may help them on different aspects of the development of software for management power systems. So I'm going to give a little bit of an introduction. Like I presented at the very beginning, 100 years ago, the same thing happens with the electric power system. So you have now the weather system and the electric power system, and they started locally, whereas we as meteorologists started globally, or at least hemispherically. Here they started with grids that were only active in big cities like Berlin or in Germany, several other cities. In fact, in 1912, they started to think about going from town to town, the transmission of power. And so here is a picture of the 110 kilovolts transmission line in Europe. This is still there and still transmitting. But 100 years later, we now transition to what is called clean energy. And those are driven by agreements in this reduction of fossil fuel burning, and also it's driven by the reduction in the cost of renewables and the expansion of electric systems in general, including the electric vehicles fleets. And so those things are impacting the power grid industry. Now the power grid industry is more tied to meteorology in many aspects. First, on how to deal with complex systems. So I'm just showing here a small town. Probably some of you know the University of Maryland, where I got my graduate courses here, College Park. Just to give you the dimensions, this is a 2 by 2 kilometers. And these systems are dynamic. So they are changing every second. And if you introduce perturbations like the intermittence of solar energy, then you get into trouble. So here, this map collects areas where you cannot, for instance, in this black area over here, you can, let's see. It's hard to see, but this area near the northern part, well, in central DC, it's not possible to install more solar energy. So red colors means it's not recommended to install there because of the system cannot hold the variability that is brought by solar energy. So only those regions that like green regions are the ones where you can install wind, solar PV farms. Something similar can be created for wind farms, but they need to have an understanding of the variability of the wind in order to determine at the street level how the electric system will react. So those are complex systems that also the meteorological field has addressed. Remember what we do in numerical weather prediction, when we decrease the resolution of the model, we actually parameterize what is inside of that cell. So the question here is how to create what it's called feeder models or representative values or nodes that represent the entire behavior of an area. So those are aspects that still are waiting for people interested on systems simplification, complex system simplification that might be interested. So why we need to simplify the grid? Well, first for visibility, but second, in order to manage it. And the actual grid is very complex, very large. The good thing is that compared to the weather system, it only has two independent variables. So the state of the system can be computed only by the voltage on each node and by the voltage phase. And so if we were to have observation of on each node, which we don't have, then we might be able to instantaneously determine the state of the actual grid. So, but that's not possible. So what we do is do simplifications. And then the intention is to create what is called digital twins. These digital twins reflect, it's like the model of the real system. It's also a dynamical state observer that could be observed. One could do parameter tuning, and we can start doing both data-driven, and also one could actually run the numerical prediction systems with a system like this. There are several requirements that makes this kind of different. One is that this affects or impacts directly household and the economy specifically. And so these have to be sustainable for the environment, the social, and from the business perspective. So investors could actually, or people invest on their panels and so on. So those are things that have to be taken into account. It must be accessible. That means currently our, most of the power grid is actually centralized. And the intention is to have microgrids, so they can by themselves govern a small section of the energy. They have to be reliable and resilient to be able to withstand these conditions, weather conditions, including severe weather, and they have to be affordable. That means one has to have a knowledge in advance of the weather and the resources to make a good judgment of how much of reserves we have to have before a weather event occurs. So in other words, the integration or the interacting of weather technology into the power grid is something that it's still open. We have mesoscale models like this operational model and relatively better forecasts, at least with the when we have enough observations to calibrate the model. And the impact sometimes is handled in a statistical manner because we don't have actually something associated with the grid itself. So basically, we ignore the interaction itself with the grid. I'll explain in a minute what I meant. But the impact that weather has not only around the world is that every big storm produces outages. And when you have big storms like a hurricane in the US, here in the New England and Northeast area, people get affected. And these are like more than 8 million households or in industries that are affected during the hurricane in 2012. And this curve, or this the decrease, means that the outages and the system is coming back to service. So how fast this goes, it's very important because some critical infrastructure require to have energy like continuously. So the fact that it takes several days to recover is not good. So the intention is to decrease the rate very quickly, or as quickly as possible. And so that's one of the issues that not connecting or not having the state of the grid on time and methods to predict how to repair it or how to put it online, we call it, is one of the main issues or challenges of the next decade. Especially now that with this realization that climate change induce more often this type of extreme weather conditions. Here is what happens with Hurricane Sandy in terms of the economic side. let's put aside for now the impact in human loss or other damages. Here is we call it loads, basically the demand. So the demand that must be met by the energy supply. When Sandy hits the New Jersey state or the Northeast, you see that there is still demand because some of the customers still they have power, but there is a decrease. And there is especially a disruption in the supply demand balance, for instance, and this is reflected in the electricity price. Here you see that the price is decreased because there is an oversupply of generation. So that's a big problem. So the operators need to curtail or stop generating energy because of the power lines are down, so they don't need to generate more. And so there is an excess of energy, and that's why you see the price going negative, actually lower. Then the following day, you can see now the reverse. Now that the system is, all the houses and industry starts to get into in normal conditions, then there is a typical over demand and there is not enough supply. So those imbalances induce a price of like 100 times more expensive than what it used to be in normal conditions. So all these impacts have a downstream economical effect on the electrical power. Again, the interacting of a weather system with power grid can be also, at least from the sketching perspective, can be seen as two types of systems. In this case, you have a system that you could see one-dimensional track of the storm affecting a graph or a two-dimensional distribution. And from there, you might be able to, this is not the street level, each of these nodes is not the street level conditions, but it's actually a representation, model representation of your, what is called this is called feeder model. That means representative system. So how the interaction, the timing of this passage of the storm affects individual households, especially those who have renewable energy installed, like PV or wind, relies on what's called household energy management systems, and they have to be aware of the weather at the local level. And these are things that currently are done statistically because it's not aware of the weather yet. So those are systems that expect meteorologists to get a hand on. And here is a possible dynamic restoration. That's another problem, which once this the storm crosses this model of nodes, and so just 1 second. Well, this system or weather system impacts the supply and demand on the grid, and so creating, first of all, visibility of these systems will allow to have a rapid reaction or a rapid management to have this repaired as soon as possible. So here is the nodes that are being damaged by the storm, and then which are then later which of them are repaired, and so on. If we were to know like 2 or 3 days or even a week in advance that a system could impact certain region, then it could help to request a crew to locate to be located on strategic places such that they could much faster repair the grid. So this is another requirement for high resolution modeling to be able to do predictions beyond a few days or even weeks, to be able to have enough crew to repair the models, to repair the system. So let me see, I have 10 minutes more just to do brief conclusions. So the job is still unfinished, both in the generation and improvement of model simulations, both of the weather system and the electric systems. We need more sophisticated uses of products, and there is this new emerging well, let's say, I would say, a demand on predicting the dynamics of and the interaction of the electric grid, which is the built environment, with the weather. So those are aspects in general that I would like to bring in this discussion. Any question?
Gracias, Malaquias. ¿Tenemos alguna pregunta? Sí, Pedro.
Gracias, Malaquias, por la presentación. Una pregunta que tengo, digamos, tengo varias, digamos, pero una que digamos, de esta última parte de la presentación es, me preguntaba qué perfil de, digamos, cuál es el perfil de la gente que trabaja en el laboratorio en el que usted está y en la Universidad de Connecticut, si son principalmente gente que viene de la ingeniería o gente que viene de las ciencias de la atmósfera, digamos, o digamos, con un background en investigación en clima, digamos, un poco como el sur.
El departamento es en Environmental Engineering, en Civil and Environmental Engineering. At the graduate level, cuando uno contrata, o bueno, cuando uno tiene estudiantes, bueno, para empezar, los profesores tienen disciplinas múltiples. En mi caso, mi énfasis es en cuanto a aplicar la meteorología a problemas del medio ambiente. No hay mucha gente que salte de una área a otra. La mayor parte, o bueno, el 40% son químicos environmentalists, es decir, químicos que se dedican a las partes de contaminación, y el otro es relacionado con la contaminación del agua. Entonces hay un grupo grande, hay otro grupo de análisis de transporte, contaminación del aire. Todos ellos usan también meteorología, pero no hay una persona que sea meteorólogo todavía. Y sin embargo, mis estudiantes todos son de áreas diferentes a ingeniería del medio ambiente. Por ejemplo, tengo una estudiante que es economista, uno que es ingeniero en hidrología, uno que es oceanógrafo, y dos que son de environmental, pero están especializando en el weather. Y digamos, todos ellos finalmente tienen que aprender de alguna forma modelar. Eso es lo que nos conecta, yo creo que a todos. Y no sé si eso responde a tu pregunta.
Sí, perfecto.
Gracias. ¿Alguna otra pregunta? Si no, seguimos con Pedro.
Sí, tengo otra pregunta más. No, me impresionó mucho, digamos, la presentación, hay varios aspectos de la presentación, digamos. Una que me preguntaba era si los modelos estos que ustedes usan o desarrollan generan, digamos, la parte climática y la parte, digamos, de consumo de energía, digamos, o es simplemente, digamos, si combinan, digamos, los modelos de clima con los modelos más como de ingeniería de consumo energético, digamos, o son únicamente modelos climáticos. Digamos, esto no me queda claro, digamos, a veces me daba dudas, digamos. Si usted...
Sí, gracias por preguntar, muy buena pregunta. Hay varias formas de modelar, ¿no? Hay modelos que son long term y de largo plazo que pueden utilizarse, digamos, estadísticamente, postprocesando, y hay modelos que son de muy alta resolución. Así que aquí me estoy especializando, o en esta presentación estoy hablando de modelos operativos, es decir, que corren por ejemplo, cada 15 minutos. Entonces son modelos muy finos en cuanto a resolución, y la intención es cubrir esa área de nowcasting que generalmente utilizamos de manera también estadística, pero queremos introducir modelos que puedan resolver esa variabilidad o intermitencia en la energía. Definitivamente estamos también interesados en nosotros, modelos a largo plazo, y tenemos una propuesta de proyecto que estamos utilizando datos del CIMIP6, que es de cambio climático, para determinar los cambios en energía, especialmente eólica, en la región de Estados Unidos. Y también es otra área que se puede expandir, hay muchas preguntas ahí. No estoy muy familiarizado en esa área, pero definitivamente hay algo que se pueda colaborar también.
Gracias. ¿Alguna pregunta más? En el chat no tenemos.
Sí, yo sigo con las preguntas. Y la parte, digamos, digamos, como de impacto en la red de consumo de energía también está incluida en los modelos, o eso, digamos, eso, digamos, está por fuera, digamos, de lo que ustedes hacen, digamos. Sería claro. Sobre todo, me preguntaba en esas últimas diapositivas que presentó con las grillas, eso que parecen sistemas, con las ciudades y eso, digamos.
Sí.
Si eso también lo modelan o...
Sí. Eso, gracias otra vez. Esta es otra pregunta muy importante, y la otra mitad de mi grupo soy también parcialmente, estoy afiliado al departamento de energía y cómputo, y ahí tengo 2 estudiantes que estamos trabajando en la parte del despacho de energía. Entonces ahí hay modelos y bueno, lo que llamamos optical flow system. Y déjame mostrarte algunas cosas que no mencioné, pero tenemos un modelo que nos ayuda a determinar cómo va a ser la mezcla de energía más óptima para cada 10 minutos, ¿no? Entonces, esa es una área que también la estamos desarrollando. No quise dar énfasis en eso, pero uno de los problemas que tenemos es en el cómo mantener uno de los principales costos en la energía, especialmente renovable, es lo que le llaman mantener energía suficiente por si hay cambios repentinos. Entonces, digamos que la mayor parte de las empresas que venden energía, bueno, los operadores de energía, ellos tienen que mantener una reserva de aproximadamente 40% de energía en todo el tiempo. Entonces están gastando fuel están desechando energía en tiempo real, que no la usamos simplemente porque está ahí solamente para en caso de que uno de los sistemas falle, ¿no? Y muchos de esos fallos están relacionados con el weather. Entonces, simplemente el poder predecir con mayor certeza, digamos, medio grado de temperatura en una ciudad, tiene un impacto económico muy grande, porque entonces la cantidad de reservas puede reducirse y eso hace que digamos, ya no se tenga que generar tanta energía, porque uno de los problemas que tenemos es que generamos un exceso enorme. Argentina genera enorme energía y el problema es que no la puede distribuir porque si no hay demanda, no la distribuye, pero también ellos mantienen por regulación un exceso, que es una reserva. Entonces la reserva es por la incertidumbre que tenemos de los pronósticos. Sí tenemos modelos, le llamamos modelos de despacho, y tenemos Optimal Flow Dynamic Models que también estamos trabajando. Pero en todos ellos no tenemos, utilizamos todavía procesos estocásticos para hacer lo que le llaman Energy Management Systems, que tienen que tomar decisiones en menos de un minuto. Entonces, ¿cómo acoplar, digamos, modelos de turbulencia en estos Energy Management Systems? Es algo que todavía no está, digamos, establecido, por ejemplo, en estos HEMS, pero digamos que hacia allá sería un buen objetivo en los siguientes años.
La última, Pedro, que nos estamos quedando sin tiempo, pero sí. Había un comentario. Juan levantó la mano, podemos ir con Juan Ruiz desde Zoom.
Hola, ¿qué tal?
Hola,
No
Juan.
sé si se me escucha bien. ¿Qué tal, Malaquías? Un gusto verte. Muchas gracias por la presentación. Mi pregunta tenía que ver con el tema del field alignment que mostraste en una de tus diapositivas.
Sí.
Si por ahí me lo perdí, pero si podías comentar cuál había sido el impacto que habían tenido con esa técnica. Y con qué, si lo probaron entiendo, con tormentas tropicales o con algún otro tipo de sistemas y con qué datos
Sí,
lo utilizaron.
sí, tenemos dos publicaciones que puedo enviarte más adelante. Una es sobre el impacto que tiene digamos, en reducir el root mean square error de de tormentas tropicales. De hecho, tenemos 3 o 4 estudios que muestran que se reduce, no sé si significativamente, pero en gran proporción, como el 40% del error sistemático, si tú divides el error en error de amplitud y en error de desplazamiento, casi el 40% al menos es de desplazamiento. Entonces, ese es el error que tratamos de reducir. Y el problema que tenemos, y lo hemos hecho solamente para 500 hectopascales a ese nivel. El problema que tenemos, y es parte de este proyecto, es cómo hacerlo para el océano, porque el océano ahora tiene una topografía que, especialmente en la frontera, que hace que nuestro método no sea tan bueno. Entonces, ahorita estamos en la parte de cómo lidiar con las paredes laterales. Pero funciona muy bien a nivel de 500, bueno, a niveles altos de la atmósfera. Y de hecho, ahí parece que hay otros grupos que ya están trabajando en eso. Aquí en NOAA, en NCAR, sé de un par de grupos que también están interesados en el método, pero sí, te puedo mandar más referencias al respecto.
Muchísimas gracias.
La última, ahora sí, de Pedro, que nos están por echar del aula.
Bueno, perdón, la última, ¿para qué? Quería preguntar si tuvieras que decir cuáles son las principales dificultades para aplicar algunos de estos modelos que tienen en la parte del consumo, digamos, de la red eléctrica. Entonces, ¿cuáles son los principales desafíos de esos tipos de modelos para aplicarlo en otros lugares que no sean, hablaste de Maryland, digamos, que sean otras ciudades que no son las que tenés parametrizadas? ¿Cuáles serían los desafíos?
Sí, uno de los desafíos que tenemos en meteorología es lo que le llaman el problema de multiescala. Cuando hacemos pronósticos de flujo de energía, si usamos cada 15 minutos, y esto sería real-time forecast como cada minuto, y los valores actuales que están en color negro, este sería el power flow, el target o la observación. Y puedes ver que en real time sí podemos hacer buenos pronósticos, pero querer hacer pronósticos a 24 horas es un problema que todavía no está resuelto. Hay mucha incertidumbre, muchos errores, y es porque los pronósticos tienen muy baja resolución, los pronósticos de mesoscala, y hay obviamente necesidad de incrementar la resolución a cientos de metros para poder detectar las variaciones. Y lo otro es de que pronosticar el flujo a 100 metros es casi imposible. No hay verdaderas técnicas de hacerlo, solo lo que yo conozco son las de Machine Learning, y es una de las tareas que estamos intentando de conectar lo que se aprende de los fenómenos o de la tendencia de la serie de tiempos, cómo se puede reutilizar para hacer pronósticos a un día, por ejemplo. Entonces, y cómo le llamamos modelo de optimización de flujo puede tomar en cuenta le llamamos hierarchical power flow method. Quiere decir cuánto le dan prioridad a lo que el modelo aprendió en el pasado para hacer proyecciones online del futuro. Entonces, uno de los retos que veo es, otra vez repitiendo, que nuestros modelos actuales de mesoscala no reflejan la variación energética que corresponde a cientos de metros. Y la otra es el pronóstico del tiempo. O sea, el pronóstico del tiempo a 100 metros o 200 requiere bastante más, al menos uso de cómputo para poder tener esa resolución en espacio y tiempo.
Bueno, muchas gracias, Malaquias, gracias por las preguntas. Vamos a aplaudir para... Gracias por tu charla. Bueno, acá para agradecer también a todos los que nos acompañaron durante el año. Este fue nuestro último coloquio del 2022, así que los esperamos el año que viene con un nuevo ciclo. Muchas gracias por venir.
Bueno, muchas gracias.